Okay, so welcome guys. So in this video, let's talk about this famous Vandermonde matrix. Okay, so in this video, this is called a Vandermonde matrix, right? So it's somebody, if you take a matrix and then you take its determinant, and this is 1, 1, 1, x1, x2, x3 up to xn, and x1 square, x2 square, x3 square up to xn square. And n minus 1 to xn minus 1. Okay, so this is called a Vandermonde matrix. Basically, people like to ask about its determinant. Okay, so before I start, maybe we see some stupid example. So let's say n equals to 2. So you get this one, right? So 1 x2. So the determinant will be just x2 minus x1. Okay. Oh, by the way, so usually these determinants are called the Vandermonde's polynomial. Okay, I think. So for this one, it's a little bit cumbersome. X1 square, x2 square, x3 square. Okay, so one can easily, let's say, so you can add, right? You can times the -1 add it to the second term. That's also the second rows. So you get 0 x2 minus x1, x2 x minus x1 square, or you get 0, and then you do the same thing for the third row. Right, so you get x2 minus x1, x3 minus x1, and you'll see if you do this, then you'll somehow like this original become this, right? This original determinant become like 0, 1, 0, 1, 1, x3 plus x1, 1, x2 plus x1, and you compute the determinant of this. This is just x3 minus x2. So final result will be x2 minus x1, x3 minus x1. x3 minus x2. Okay, so hopefully you guys see some pattern. Okay. Okay, although this looks difficult. Okay. Okay, so let's talk about the general results, right? So usually the general, let's say Vn, right? The general determinant will be this one. So it's j minus i, and 1 from I, j up to n. Okay, so the purpose of this video is just prove this fact. Okay, so let's quickly see determinant v2. So v2 will be x2 minus x1, right? There's only 2. How about determinant v3 will be, right? So you get the, let's say you get the 1 minus I from 3, right? So xj minus xi, right? So you get the x3 minus x1, x3 minus x2, and also x2 minus x1, right? That's all you get, which is exactly the same. Okay, so the idea is that we hope to prove this, right? So if you guys see some other people do, so one people can do is that you keep doing the row and the matrix, you keep doing the row and column operations, and hopefully you're smart enough and find a way that such that oh, you get this answer. You can find a way that maybe you times the -1 and use the second row to minus the first row, third row minus first row, nth row minus first row, and they do the same thing and keep doing. And if you're smart enough, then probably you get this, right? But in this video, I want to directly prove this is exactly the answer, and it's the only answer it can be. Okay, so let's dive into proof. So proof is basically from the uniqueness of the polynomial. Okay, so the idea is that it's 1, 1, 1, 1, right? x1, x2. So we need to use the property of the determinants, right? So one property of determinant is that right, if I replace xj to be xi, right, for j is not equal to I, then I will always get 0, right? Suppose I replace x2 by x1, right? Then these two will be the same. Then the first two rows will be the same. If I replace x3 by xn, then you will always be the same, right? So that means from the uniqueness of polynomial factorization, I already know the answer must be this. Right? Because for any j and I, you always become this, right? So, and also for each, for xi, right? For x1, the answer is what? The answer is polynomial with x1 degree n minus 1, right? If I expand this, so total it has only n minus 1 degree, right? Which is exactly the same as this factor, right? If you only care about x1, right? So the only remaining part is that there may be constant c. So idea is that the answer, the candidate answer must be xc times, let's say, x2 minus x1, x3 minus x1, x3 minus x2, or x4 minus x1, x4 minus x2, and x4 minus x3. Okay, so if you see the power of x1, right, you get 1, 1, 1, right? So total you will get n minus 1. So for each x2, you get n minus 1, you get x3, you get n minus 1. So you see that the degree, so the degree already match, and it match all the roots, right? So this is the total. This is the only possibilities that it can be, right? Because it already saturate all the roots. So there's no other place to place. There's no other place to put any other polynomial gx1 to xn here because the degree is already saturated, right? So the only possibility is that there is a constant c here. Oh, so the idea is that what is a c, right? What is c? So what is c? Okay. So the trivial, right? If I expanded I know that there's always one term for diagonal, right? If I do the expansion, so there's one term is x2, x3 to the power square, x4 to the cube, let's say xn minus 1, right? But if you see expansion, this is exactly 1x2, 1x3, 3x4, right? So it already here, right? So this term the coefficient of this term must be 1, right? By this expansion 1, so answer c must be 1, right? C must be 1. Because he already matched this term, and this term is unique, right? So a constant term, so the constant between this term must be 1, and he already shown 1, right? So c must be 1. So c must be 1. So from here we know that we do not use any row operations or column operations, but from the uniqueness and the factorization and the property of determinant and the match coefficient, we already know this is the unique determinant of the Vandermonde matrix. Okay, that's the purpose of this video. I hope you guys like it. Be sure to subscribe to my channel. I will see you guys in the next videos.